At first, 3I/Atlas looked like a threat written across the dark. It had arrived from beyond the solar system, crossed the region of the planets, and was moving too quickly for the sun to keep it. By the time astronomers understood what they were watching, the visitor was already following a path that would carry it away forever. But it was never coming for Earth. At its closest, 3I/Atlas remained about 1.8 astronomical units from our planet. 1 astronomical unit is the average distance between Earth and the Sun. Even at its nearest point, this comet stayed farther from us than the Sun does. It did not present an impact danger. Its coma, its tail, and the gases released as sunlight warmed its surface all behaved like the activity of a natural comet. There was no need to turn it into a weapon, a warning, or a machine. The real mystery was quieter and far more difficult to understand. Inside the water, carbon compounds, and other material escaping from the comet, astronomers found unusual versions of familiar atoms. These isotopes formed a chemical pattern unlike the patterns normally measured in comets from our own solar system. The differences were not merely curious details. They suggested that the ice had formed in an exceptionally cold environment and had preserved evidence from a less chemically enriched period in the history of the Milky Way. When researchers compared those measurements with models of how the galaxy changed over time, an extraordinary possibility appeared. 3I/Atlas may have formed roughly 10 to 12 billion years ago. If that estimate is correct, the comet could be more than twice as old as the solar system. It may have become solid matter billions of years before the Sun, Earth, or any familiar planet existed. That does not mean its age has been read from a perfect clock. No instrument has found a date hidden inside the ice. The estimate depends on measured isotope ratios, an understanding of cold chemistry, and models describing how generations of stars gradually changed the composition of the galaxy. The measurements are real. The formation conditions are strongly constrained. The precise age remains an inference, and every step in that inference must be examined. This is where the unsettling part begins. For most of human history, comets belong to the family of the Sun. They could travel on long, dark orbits, disappear for centuries, and return. But they remain tied to the same gravity that holds Earth. 3I/Atlas broke that familiar picture. It entered with speed left over after the Sun's gravity was accounted for, and it will leave with that freedom intact. Its visit was not a return. It was a single crossing between unrelated systems. We saw it only because its path happened to pass through our neighborhood during the brief period when our telescopes were capable of recognizing what it was at all. 3I/Atlas was harmless because it stayed far away. Yet the history it may carry reaches into a time when the Milky Way was younger, when the Sun had not formed, and when unknown planetary systems could already have been building worlds. Whatever star once held this comet is not identified. Whatever planets may have shared its birthplace are beyond recovery. After billions of years between the stars, only this small fragment entered our reach, released part of its frozen material, and allowed distant instruments to read it. So the central question is not whether 3I/Atlas came to destroy us. It did not. The question is how a comet passing through the solar system can reveal when and where it formed, and whether its chemistry truly makes it a surviving piece of an ancient planetary system. To answer that, we must separate what astronomers directly observed from what they inferred. We must begin with the moving point of light itself, follow the measurements that proved it came from interstellar space, and then descend into the atoms released from its ice. Only after rebuilding that chain can we decide how old this visitor may be, what kind of lost environment produced it, and why a harmless object can still leave us facing a history almost too large to imagine. The story begins with a survey designed to notice change. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System detected a faint object in images taken from Rio Hurtado, Chile. The survey is known by its initials, ATLAS. Its telescopes repeatedly photograph wide areas of the sky, looking for points of light that move against the distant background. Most detections belong to objects already living inside the solar system. Some are asteroids. Others are comets. A new point of light is therefore not immediately treated as a visitor from another star. It must first become a measured path. That path begins with position and time. In one image, an object appears at one location. In a later image, it has shifted. Additional observations reveal how quickly it is moving and how its direction changes under the pull of the sun. Astronomers combine those positions and calculate an orbit that could connect them. With only a short series of observations, several possible paths may still fit. As more measurements arrive, the range narrows. 3I/Atlas quickly became unusual because the path that best matched its movement did not look like the closed orbits of familiar asteroids and comets. It appeared to be passing through the Sun's domain rather than traveling around it. But an early orbit is never accepted merely because it produces an exciting answer. Measurement errors, a short observation period, or missing earlier data can distort the first calculation. The solution had to become stronger. That strength came partly from precovery images. Precovery means finding an object in photographs taken before its official discovery. Once astronomers know where an object was later seen and have an early estimate of its motion, they can search older observations for the same faint point. Each recovered image extends the period over which the object has been tracked. Instead of describing only a short piece of its journey, the measurements begin to show a longer arc. This matters because an orbit is not a line drawn through the sky by guesswork. It is a physical solution that must explain every reliable position at every recorded time. A path that seems possible across a few nights may fail when an earlier image is added. A path that continues to match as the observation arc grows becomes much harder to dismiss. In the case of 3I/Atlas, the extended record supported an orbit that was not bound to the Sun. The object eventually received the designation 3I/Atlas. The letter I identifies it as interstellar. The number 3 places it in an exceptionally small group. Before it, astronomers had confirmed only 2 objects arriving from beyond the solar system. The first was 1I/Oumuamua, discovered in 2017. It passed through quickly and showed no ordinary cometary coma that could provide a rich sample of released gas. Its shape, motion, and limited observing window created questions that remain difficult to settle. The second was 2I Borisov, discovered in 2019. Borisov displayed clear cometary activity, making its natural character and chemical study more direct. Together, those objects proved that material from other planetary systems could enter ours. Yet 2 examples could reveal very little about how varied that material might be. Then came the third. For astronomers, a sample of 3 was still painfully small, but it created comparison where almost none had existed. Similarities could now look less accidental, while differences could reveal how many kinds of distant systems release debris. 3I/Atlas was not important simply because astronomers had counted one more visitor. It offered another chance to study matter formed around an unknown star, and its visible activity gave researchers access to gases released from its ice. It also arrived with motion that made its outsider status increasingly clear. Still, at this stage, the label interstellar answered only one question. It said that the comet was not a permanent member of the solar system. It did not say which star had once held it, how long it had traveled, or when its material first became solid. Those distinctions are essential. An object can come from interstellar space without being ancient. A planetesimal might be ejected soon after its system forms, or much later after a gravitational disturbance. It may wander for a short interval or for billions of years. Its current motion records the fact of arrival, but not a complete history of everything that happened before it entered the sun's influence. Even the word comet describes only part of what astronomers observed. It refers to the activity produced as buried ices warm and release gas and dust. That activity shows that 3I/Atlas carries volatile material, unlike a completely inactive rock. It gives the object a coma and makes chemical measurement possible. But activity alone cannot establish an interstellar origin. Comets born around the sun also grow comas when they approach its warmth. The classification therefore rested on two separate ideas that must not be confused. Its activity identified it as cometary. Its trajectory identified it as interstellar. One described its physical behavior. The other described its relationship with the sun. By combining new observations, earlier images, and repeated orbit calculations, astronomers moved from a faint detection to a confident classification. What began as a small shift between photographs became evidence of an object crossing the solar system only once. The discovery was not a dramatic instant when every answer appeared. It was a sequence in which each additional position restricted the possible story until an ordinary solar system orbit no longer worked. But saying that the orbit was unbound is not enough. The phrase must be given physical meaning. Could the planets have thrown a local comet onto such a path? Could uncertainty in the measurements still account for its apparent escape? And what do its speed, direction, and closest approaches actually prove? Those questions lead away from the discovery images and into the dynamics of the encounter. To understand why 3I/Atlas earned its interstellar name, we must examine the orbit that refused to close around the sun. Most objects moving around the sun follow closed paths. A planet travels on a nearly circular orbit. A long-period comet may follow an extremely stretched ellipse, spending most of its time far beyond the planets before falling inward and returning to the dark. The shapes differ, but the relationship is the same. Each object is gravitationally bound. Unless something changes its motion, the sun can call it back. 3I/Atlas followed a different kind of path. To understand the difference, imagine an object falling toward the sun from a great distance. Solar gravity accelerates it as it approaches. After the object passes the sun, that same gravity slows it as it climbs outward. A bound object may move very quickly near the sun, but it does not keep all that speed. In principle, if its motion could be followed far enough away, its remaining speed would fall toward the value allowed by its closed orbit. An interstellar object arrives with motion of its own. The sun accelerates it on the way in and removes the same gravitational gain on the way out, yet the object still has speed left over. Astronomers call this the hyperbolic excess velocity. For 3I/Atlas, that excess speed was about 58 kilometers per second. Even after the sun's contribution is accounted for, the comet remains fast enough to escape permanently. That is why its speed near the planets cannot be explained simply by saying that it fell toward the Sun. Every comet accelerates while falling inward. The important question is what remains after solar gravity has been removed from the calculation. In the case of 3I/Atlas, the answer was an enormous residual motion, one that a returning solar system comet would not possess. The shape of the calculated orbit expressed the same fact in another way. Orbital shape is often described by a number called eccentricity. A perfect circle has an eccentricity of 0. An ellipse has a value between 0 and 1. A parabolic escape path has a value of 1. A hyperbolic path has a value greater than 1 because it does not close around the Sun. The eccentricity calculated for 3I/Atlas was about 6.14. This was not a value sitting barely above the boundary, where a small error or an earlier planetary encounter might create doubt. It was deeply hyperbolic. As observations extended the measured arc, the unbound solution remained. The comet was not a local object, nudged slightly beyond escape. It had approached the solar system already carrying interstellar speed. Its direction added another distinctive feature. The orbit was inclined by about 175 degrees relative to the main plane in which the planets travel. An inclination near 180 degrees means the object moves in a nearly retrograde direction, crossing the planetary region almost opposite the usual direction of planetary motion. This geometry is not, by itself, proof of interstellar origin. Some solar system comets also travel on steep or retrograde paths. But combined with the extreme hyperbolic orbit and high excess velocity, it helped describe an encounter unlike the return of a bound comet. Could a planet have produced this path? Planets can strongly disturb small bodies. Jupiter, in particular, can redirect comets and sometimes eject them from the solar system. But such an explanation must match the history and geometry of the orbit. A local comet thrown outward would show that its decisive acceleration occurred during a suitable close encounter. 3I/Atlas was observed arriving on an extreme unbound trajectory. Its incoming motion already contained the excess speed. The planets did not manufacture its interstellar character during this passage. The orbit also established where the object would go. 3I/Atlas reached perihelion, its closest point to the Sun, at about 1.36 astronomical units on October 29, 2025. That placed perihelion outside Earth's average orbital distance from the Sun. The comet then continued outward along the other branch of its hyperbolic path. Unlike a periodic comet, it has no distant turning point that will eventually send it back. The Sun will slow it, but not enough to reverse it. Its closest approach to Earth was even more reassuring. The comet remained roughly 1.8 astronomical units away, about 270 million kilometers. Distance alone can be difficult to feel, but the astronomical unit comparison makes the scale clear. Earth is 1 astronomical unit from the Sun on average. At its closest, 3I/Atlas stayed farther from Earth than the Sun is from Earth. Its calculated path did not place our planet in danger. This safety conclusion did not depend on whether the comet was large or small. An impact threat requires an orbit that intersects Earth at the relevant time. 3I/Atlas had no such trajectory. Uncertainty about the exact diameter of its hidden nucleus could affect estimates of its mass or activity, but it did not turn a distant passage into a collision course. The orbit therefore produced a firm local answer. 3I/Atlas was an outsider. It arrived on an unbound, deeply hyperbolic path, crossed the solar system at high speed, remained safely distant from Earth, and will continue back into interstellar space. Its motion could tell astronomers what it was not. It was not a permanent member of the Sun's comet population, not an object captured into a returning orbit, and not a visitor created by a planetary ejection during this encounter. This was a temporary encounter, not the opening movement of a repeating celestial cycle. But even a precise orbit has limits. It can be extended forward to show that the comet will leave, and backward to describe how it entered the solar system. It cannot be traced reliably across billions of years to one lost star. The Milky Way is filled with moving stars, clouds, and gravitational disturbances. Over immense time, small uncertainties grow until a unique route disappears. Most importantly, speed is not a birth certificate. An old object can move quickly, but motion alone cannot establish when its ice formed. A younger body ejected under different conditions might also cross interstellar space at substantial speed. The orbit proves foreign origin with high confidence. It does not prove the proposed age of 10 to 12 billion years. To search for that deeper history, astronomers needed information carried by the object itself. Fortunately, 3I/Atlas did not remain sealed. As sunlight warmed it, frozen material began escaping into space. The same activity that surrounded the nucleus and complicated measurements of its size also lifted molecules into view. The orbit had proved that the sample came from beyond the solar system. The next challenge was learning how telescopes could turn its glowing coma into a remote chemical sample. The solid heart of a comet is difficult to study even when the comet belongs to the solar system. It is small, dark, distant, and surrounded by material that can become far brighter than the object itself. For 3I/Atlas, those difficulties were intensified by speed. Astronomers had only one passage in which to observe it. There would be no return years later and no second opportunity under the same conditions. Yet the comet carried its own method of revealing what lay inside. Far from a star, volatile materials can remain frozen within a comet's nucleus. As the object approaches the Sun, its surface receives more energy. Some buried ices begin to change directly from solid into gas. This process is called sublimation. Escaping gas drags dust away from the surface, producing a growing cloud around the nucleus. That surrounding cloud is the coma. Solar radiation and the flow of charged particles from the Sun can then push gas and dust outward, creating tails. The visible comet is therefore much larger than its solid body. A nucleus that may span only hundreds of meters or a few kilometers can create a coma extending across an enormous volume. The extra brightness makes the comet easier to detect, but it also hides the boundary of the nucleus. A telescope sees light from dust and gas layered around a much smaller central object. Separating those contributions requires models, and different assumptions can produce different size estimates. For that reason, the diameter of 3I/Atlas should not be reduced to one confident number today. Observations constrained it to a broad range, commonly extending from hundreds of meters to several kilometers. The exact value remained uncertain because the active coma contaminated the light that would otherwise come from the nucleus. This uncertainty did not weaken the orbital conclusion. A hidden nucleus could be larger or smaller without changing the measured fact that the comet was safely distant and unbound. Size mattered for questions about mass, surface behavior, and the amount of material being released. It did not determine whether the object came from interstellar space. More importantly, the same coma that concealed the nucleus exposed its chemistry. Every molecule interacts with light in particular ways. A gas may absorb certain wavelengths or emit light at a set of recognizable wavelengths. When astronomers spread the comet's light into a spectrum, those patterns appear as features that can be connected to specific molecules. The technique does not scoop material into a container, but it allows distant instruments to identify substances carried away from the nucleus. This turns cometary activity into a form of remote sampling. The sun supplies heat. The nucleus releases material. The coma spreads that material across a larger area. Telescopes collect its light, and spectrographs separate the signal into chemical information. A body that no spacecraft could reach during its brief passage begins to reveal parts of its interior across interplanetary distance. No single telescope could answer every question. Different molecules produce useful signals at different wavelengths, and every instrument has its own sensitivity, resolution, and observing limits. The study of 3I/Atlas therefore became a coordinated campaign in which several facilities examined different parts of the same event. Hubble contributed high-resolution imaging that helped constrain the nucleus and describe the surrounding activity. Its images could follow changes in the coma and tails while limiting how much light might come from the hidden central body. But imaging alone could not provide the complete chemical story. The James Webb Space Telescope offered powerful infrared spectroscopy. Infrared observations are especially useful for identifying molecules through the ways they interact with heat-related wavelengths. Webb could examine gases in the coma and distinguish chemical features that ordinary visible images could not separate. Its measurements would later become central to the isotope investigation. The Atacama Large Millimeter Submillimeter Array, known as ALMA, observed at much longer wavelengths. Rather than behaving as one dish, ALMA combines signals from many antennas. This allows it to detect rotational signatures from molecules in cold gas and to study material distributed around the comet. Its independent measurements provided another view of water-related chemistry. The Very Large Telescope in Chile added detailed optical spectroscopy. Instruments there could examine features associated with carbon and nitrogen-bearing material in the coma. Because those observations used a different telescope, wavelength range, and molecular tracer, agreement with space-based results would carry more weight than a repetition of the same method. Other observatories and missions, including SphereX and spacecraft positioned elsewhere in the solar system, expanded the coverage. As 3I/Atlas moved closer to and then farther from the Sun, the strength and balance of its activity changed. Repeated observations could show which materials became dominant at different distances. Timing mattered, because a coma is not a perfectly preserved sample sitting motionless in space. Sunlight drives its release. Gas expands. Molecules can be changed or broken apart after leaving the nucleus. Dust scatters light. Production rates rise and fall as illumination and temperature change. Astronomers, therefore, had to interpret each spectrum in the context of when it was taken and how far the comet was from the Sun. They also had to distinguish parent molecules released from the nucleus from products formed after those molecules entered the coma. A signal associated with a simpler fragment may point back to a more complex source. Connecting observation to original ice requires chemical understanding rather than naming every feature as if it came directly from the surface. These limits reveal why the observing campaign mattered. A single image could show a tail. A single spectrum could identify a molecule. But multiple instruments, wavelengths, and dates could test whether a pattern remained consistent. The goal was not to make the comet appear more mysterious. It was to reduce the number of explanations that still fit the evidence. By this stage, Astronomers had established a powerful chain. Orbital measurements proved that the object came from outside the solar system. Solar heating released material that had been locked inside it. The coma placed that material within reach of spectroscopy. Different observatories then divided the problem according to their strengths. But identifying a molecule is not the same as learning its history. Water around another star can still be water. Carbon dioxide remains carbon dioxide. The deeper clues lie in abundance, behavior, and ultimately in the relative forms of the atoms inside those molecules. Before those atomic fingerprints can be understood, the ordinary chemical inventory must come first. What substances did 3I/Atlas release? How did their importance change during the passage? And how familiar was this visitor when judged as a natural comet? Once the coma became a remote sample, the first task was straightforward in principle: identify what the comet was releasing. The answer did not reveal a machine, an unknown form of matter, or chemistry beyond nature. Instead, astronomers found a collection of substances that belonged to the broad vocabulary of comets. Water was present. So were carbon dioxide and carbon monoxide. Observations also identified methane and material connected to hydrogen cyanide and the CN radical, along with dust, organic compounds, and traces of metals such as nickel. Each detection added detail to the chemical portrait, but the names alone could be misleading. Familiar ingredients do not guarantee a familiar recipe, and a molecule found in two comets may exist in very different proportions or may have experienced a very different history. This distinction matters because popular descriptions often divide discoveries into two simple categories. Either an interstellar object is ordinary, meaning it resembles material already known around the Sun, or it is alien, meaning every feature must be unprecedented. Real chemistry does not follow that division. Planetary systems form from many of the same elements and simple molecules, but temperature, radiation, location, and later processing change how those materials are combined and preserved. 3I/Atlas could therefore be natural and recognizable while still carrying an unusual record. Carbon dioxide was an important part of its observed activity. Carbon monoxide also became significant, and water grew more prominent as solar heating changed. The balance among these gases was not fixed throughout the encounter. At different distances from the Sun, different volatile materials could dominate the coma. The broad transition described in the observations moved from carbon dioxide dominance toward stronger water activity and later toward carbon monoxide dominance. That changing pattern was not random. Each ice responds to temperature in its own way. A highly volatile substance can begin escaping at a greater distance, where sunlight is still weak. Water requires stronger heating before it becomes a major driver of activity. As the comet approaches and then recedes from the Sun, changing surface conditions, buried layers, and the distribution of ice can alter which gases escape most strongly during its single passage. Water carried special importance because it offered a direct comparison with comets from the solar system. But merely detecting water did not establish whether the ice formed near another young star, inside an ancient cloud, or after later chemical processing. Ordinary water molecules contain 2 hydrogen atoms and 1 oxygen atom. To uncover a deeper history, astronomers would need to distinguish water built with ordinary hydrogen from water containing its heavier form. Carbon-bearing molecules raised the same problem. Carbon dioxide in 3I/Atlas was still carbon dioxide. Carbon monoxide was still carbon monoxide. Their existence demonstrated available carbon, oxygen, and cold volatile material, but it did not by itself identify the age of the comet. The more powerful clue would come from comparing different isotopes of carbon inside those gases. The detection of organic material also required careful language. In chemistry, organic generally refers to compounds built around carbon. Such compounds are widespread in space and occur in lifeless environments. They can form in cold clouds, on icy grains, and within the material that becomes comets. Their presence in 3I/Atlas showed chemical complexity, but it did not show that the comet carried life, biological remains, or evidence of a living planetary system. The same discipline applied to hydrogen cyanide and CN. Their names may sound dangerous or biological when heard outside a scientific context. In a cometary coma, they are chemical tracers. Their spectral features allow astronomers to study carbon and nitrogen, including the relative amounts of their isotopes. They reveal chemistry, not intent. Nickel created another opportunity for exaggeration. Metal vapor can sound artificial because humans associate refined metals with machines. But nickel is a natural element produced by stellar processes and incorporated into rocky and dusty material. Its detection did not require an engineered source. Metals can be released from cometary grains under conditions that researchers continue to study. The useful question was how the nickel fit the overall composition, not whether its name could be turned into evidence of technology. Taken together, the inventory answered a fundamental question about the object's character. 3I/Atlas behaved like an icy planetesimal. Sunlight warmed it. Volatile compounds escaped. Dust entered the coma. The balance of activity changed with distance. Its chemistry belonged to natural processes that can operate while a planetary system is forming. That conclusion was important, precisely because it removed a false mystery. The comet did not need to be artificial to be extraordinary. Its scientific value came from being natural material formed somewhere beyond the sun. A manufactured object would tell a different story. This comet offered something more basic, a sample of how another planetary environment assembled and preserved ice. At the same time, calling it a natural comet did not make it a copy of local comets. The proportions were unusual, and the atomic forms inside the molecules were more unusual still. Two blocks of ice can look similar while preserving different temperatures, radiation histories, and source material. The distinction is like reading two texts written with the same alphabet but arranged into different accounts. The letters are familiar. The history carried by their pattern is not. This is why abundance and isotope ratios matter. Abundance asks how much of one substance exists compared with another. It can reveal which ices dominate and how activity changes. An isotope ratio asks how often one version of an element appears compared with another version. Because isotope chemistry responds to temperature and to the changing composition of the galaxy, those ratios can preserve clues that the molecular names cannot. The inventory therefore produced a provisional answer. 3I/Atlas was not chemically alien in kind. It contained recognizable cometary materials, including water, carbon-bearing volatiles, nitrogen-bearing species, organics, dust, and metal. Its activity was consistent with a cold outer system body exposed to a new star's heat. But this answer immediately revealed its limitation. None of those ingredients carried an obvious date. Water is found in young environments and old ones. Carbon compounds can survive many settings. Organic molecules can form without life. Nickel can occur without technology. A list of substances could establish natural character while leaving the formation epoch unresolved. The deeper evidence was hidden inside the familiar ingredients. Hydrogen can appear in a heavier form called deuterium. Carbon and nitrogen also possess isotopes with different numbers of neutrons. These variations do not change an element into something else, but they can change how molecules form and react under particular conditions. In the water released by 3I/Atlas, the balance between ordinary hydrogen and deuterium was unlike the balance normally measured in solar system comets. That difference would become the first major chemical surprise. The comet's water was not simply water from another system. It was water carrying a memory of extreme cold. Water looks simple because its formula is familiar. Two hydrogen atoms join one oxygen atom, producing the molecule that shapes oceans, clouds, ice, and living cells on Earth. But not every hydrogen atom is identical. Hidden inside the water released by 3I/Atlas was a difference small enough to exist within the nucleus of an atom and powerful enough to point toward the conditions in which the ice formed. The most common hydrogen atom has one proton in its nucleus. A heavier form, called deuterium, has one proton and one neutron. Both are hydrogen because the number of protons defines the element. The added neutron changes the mass without changing hydrogen into a new element. These versions are isotopes, atoms of the same element with different numbers of neutrons. When deuterium replaces ordinary hydrogen in a water molecule, the result is often called heavy or deuterated water. It behaves much like ordinary water, but the difference in mass slightly changes the speed and preference of chemical reactions. Under some conditions, molecules containing deuterium form or survive more easily than those containing ordinary hydrogen. Over time, this can produce an enrichment that records the environment in which the chemistry occurred. Astronomers describe that enrichment using the deuterium to hydrogen ratio, written as D-H. The ratio compares the number of deuterium atoms with the number of ordinary hydrogen atoms in the sampled material. It is not a statement that every 100 water molecules contain one identical arrangement, because the measurement concerns the population of hydrogen isotopes across the observed gas. But it provides a clear way to compare one source of water with another. For 3I/Atlas, observations with the James Webb Space Telescope measured a water-DH ratio of 0.98%, with an uncertainty of 0.06%. In rounded language, deuterium accounted for about 1 part in 100 relative to ordinary hydrogen. That value was extraordinary when placed beside measurements from the solar system. The mean value commonly used for comparison with solar system comets is about 0.029%. Individual comets vary, and no single average describes every comet ever measured. Even with that caution, the contrast was enormous. The water associated with 3I/Atlas was roughly 30 times richer in deuterium than the typical comparison value. It was also far above the ratio found in Earth's oceans. The phrase 30 times needs to be understood correctly. It does not mean that every piece of the comet contains exactly 30 times the deuterium of every local comet. The comparison is between measured ratios and a representative solar system value. Different comet families show a range, and measurements carry uncertainties. The point is not a perfect multiplier. The point is that 3I/Atlas sits far outside the familiar local pattern. Why would cold conditions produce such an effect? At very low temperatures, the small mass difference between ordinary hydrogen and deuterium becomes chemically important. Reactions involving deuterium can gain an advantage because certain exchanges are easier to preserve in the cold and harder to reverse. In dense, shielded environments, ion-molecule reactions can transfer deuterium into compounds that later contribute to water and other ices. The colder the material remains, the more strongly some of these fractionation pathways can favor heavy hydrogen. Fractionation is simply the process by which isotopes become unevenly distributed. The starting material may contain only a small amount of deuterium, but chemical reactions do not always treat the light and heavy forms with perfect equality. Under the right conditions, deuterium becomes concentrated in particular molecules. If those molecules freeze onto dust grains and are later built into a comet, the enrichment can survive as part of the ice. Heat can weaken or erase parts of that record. When material is substantially warmed, mixed, evaporated, and reformed, isotope ratios may move toward new values. An extreme enrichment therefore suggests not only cold chemistry, but also limited later thermal reprocessing. The ice in 3I/Atlas appeared to have preserved a signature that would have been difficult to maintain if it had repeatedly experienced much warmer conditions. The relevant formation temperature inferred from the combined evidence was no more than about 30 Kelvin. On the Celsius scale, that is close to -243 degrees. This number does not mean every part of the comet remained at exactly that temperature throughout its entire history. It describes the very cold environment favored by the chemistry that produced and preserved the measured isotope pattern. This cold signature is powerful because it comes from matter rather than an exotic substance. The same hydrogen found throughout the cosmos becomes a record when its isotopes are counted carefully. Nothing new had to be invented. The clue emerged from a familiar molecule, carrying an unfamiliar balance of atomic mass. Such temperatures can occur in cold molecular material and in the distant outer regions of a forming planetary system, far from the heat of a young star. There, gases and ices interact on tiny grains, and a planetesimal can assemble from material whose chemistry was set before or during the earliest stages of the system. The DH measurement therefore pointed toward a frozen origin far removed from the warmer regions where rocky planets form. This interpretation did not rest on the existence of water alone. Water is widespread. The important evidence was the relative amount of deuterium, measured through spectral features and compared with known patterns. The result changed the question from, did the comet contain water, to what conditions could make water with this isotope ratio? Confidence increased because the water evidence was not limited to one instrument and one analysis. Webb's infrared spectrum provided the precise DH value central to the result. Independent observations with ALMA also found strongly enriched deuterated water. ALMA worked at different wavelengths and detected molecular behavior through a different observing system. The results were not identical copies, but they pointed in the same direction. Independent agreement matters because every measurement has possible sources of error. A spectral feature can overlap another signal. Models of gas production can depend on the shape and expansion of the coma. Conditions change as the comet moves. When separate facilities using different methods find compatible enrichment, an explanation based only on one instrument's weakness becomes less convincing. The water evidence thus delivered a strong local payoff. 3I/Atlas did not merely carry ice from outside the solar system. It carried water shaped by an exceptionally cold chemical environment. The magnitude of its deuterium enrichment separated it sharply from the familiar cometary values used for comparison. The ice appeared to have avoided enough later heating to preserve that ancient chemical character until sunlight released it near our sun. But cold is not the same as old. A very low formation temperature describes a condition, not a date. Cold regions exist at many times in galactic history. A young planetary system forming today can contain a distant, frigid disk. An ancient system could also have formed warm material closer to its star. The DH ratio can reveal chemical pathways and thermal history, but it cannot, by itself, place the comet on a calendar. This is the most important limit on the water result. It would be tempting to say that an extreme DH ratio proves 3I/Atlas formed 10 or 12 billion years ago. That conclusion would skip a necessary step. The measured ratio supports cold formation and limited reprocessing. Translating chemistry into an age requires other isotopes and models of how the composition of the Milky Way changed across generations. Later events also complicate a simple reading. Material can inherit deuterium enrichment from a molecular cloud before a star forms. It can be altered inside a protoplanetary disk. Different reservoirs can mix. A comet may assemble from grains carrying more than one chemical history. The final DH ratio is a preserved result of those processes, not a complete record of each one. Even so, the measurement ruled out the idea that 3I/Atlas was simply a local-style comet displaced into interstellar space. Its water demanded a colder and chemically distinct origin. It supplied the first strong physical clue about the environment that existed before the comet became a wandering object. To move from environment toward epoch, astronomers needed another record. Carbon offered one. Stars manufacture and redistribute carbon isotopes over time, gradually changing the material available to later generations of stars and planets. Nitrogen carries a related history. If the ratios inside 3I/Atlas differed from the modern solar system and the nearby interstellar medium, they could connect its cold ice to an earlier stage of the galaxy. The water had answered where, in a broad physical sense, somewhere exceptionally cold. It could not yet answer when. That next step was hidden in carbon from a younger Milky Way. Water had revealed an environment cold enough to favor deuterium, but the age question remained open. To approach it, astronomers turned to elements whose relative forms change as stars live, die, and return material to the galaxy. Carbon became the central clue, supported by nitrogen. Like hydrogen, carbon has isotopes. The most common is carbon-12, whose nucleus contains 6 protons and 6 neutrons. Carbon-13 has the same 6 protons, so it remains carbon, but it carries a 7th neutron. Astronomers compare them using the carbon-12 to carbon-13 ratio, written as 12C/13C. This ratio can easily be misunderstood. A higher number does not mean there is more heavy carbon. Carbon-13 is the heavier isotope, and it appears in the denominator. If the ratio rises, carbon-12 is more abundant relative to carbon-13. A value of 150 means there are about 150 carbon-12 atoms for each carbon-13 atom in the measured population. The higher the ratio, the lower the relative share of carbon-13. In the solar system, a commonly used carbon ratio is near 90. Values in nearby interstellar and protostellar material also provide a local comparison. These numbers are not identical everywhere, because the galaxy contains chemical gradients and varied environments. Even so, the ratios measured in 3I/Atlas stood well above the familiar local value. Using carbon dioxide in the coma, researchers derived a 12C/13C range of roughly 141 to 191. Carbon monoxide produced a range of about 123 to 172. The exact ranges reflected measurement uncertainty and analysis, but both pointed toward the same broad feature. Carbon-13 was relatively scarce compared with carbon-12. Agreement across two molecules mattered. Carbon dioxide and carbon monoxide do not produce the same spectral features, and their abundance can respond differently as the comet warms. If only one molecule had given an extreme ratio, questions about that particular measurement or chemical pathway would have carried more weight. Finding compatible behavior in both made the pattern harder to explain as an isolated peculiarity. Another observation strengthened the case. The Very Large Telescope examined CN in the coma using optical spectroscopy. CN is a molecule containing carbon and nitrogen. Its carbon isotope ratio was around 151, consistent with the high values inferred from carbon monoxide and carbon dioxide. This was a different molecular tracer, observed with a different facility in a different part of the spectrum. The same VLT study also measured the relationship between nitrogen-14 and nitrogen-15, finding a ratio around 363. As with carbon, the ratio describes the balance between isotopes of the same element. The nitrogen result did not simply repeat the carbon measurement, but it added another line of evidence that the comet's material did not match the familiar isotope patterns of typical solar system comets. Multiple instruments do not automatically guarantee that every interpretation is correct. Each measurement still depends on identifying spectral features, modeling the coma, and estimating uncertainties. But independent convergence changes the balance of explanation. Webb, ALMA, and the VLT were not all seeing one accidental flaw in one detector. Different molecules and wavelengths were pointing toward a coherent chemical history. Why should the balance of carbon isotopes have anything to do with the age of the galaxy? The answer begins inside stars. The early universe did not begin with the full chemical mixture found in planets and living bodies today. Stars transformed lighter material through nuclear reactions. When stars lost their outer layers or ended their lives, they returned newly processed elements and isotopes to surrounding space. Later stars formed from gas that included some of that recycled material. This process repeated across generations. The Milky Way did not become chemically rich all at once. Its gas changed as stars formed, processed matter, and redistributed it. Astronomers use the word metallicity to describe the abundance of elements heavier than hydrogen and helium. In this language, carbon and oxygen count as metals even though they are not metallic objects in everyday speech. A relatively metal-poor environment therefore contains less material produced and accumulated through previous generations of stars. It does not contain no heavy elements. A comet made of water and carbon compounds obviously requires oxygen and carbon. Metal poor is a comparison. The source material carries a lower level or a different pattern of stellar enrichment than material formed later in a more processed region. Carbon-12 and carbon-13 do not accumulate in exactly the same way or on the same schedule. Different stars and nuclear pathways contribute to them. As galactic material is recycled, the ratio between these isotopes evolves. A high 12C/13C ratio can therefore be consistent with material that formed when less carbon-13 enrichment had occurred. The chemical change is gradual, rather than a clean division between an early galaxy and a modern one. Gas from different sources mixes. Some regions form stars rapidly, while others evolve more slowly. Every new system inherits a local mixture shaped by the history around it. For this reason, isotope ratios work best as population clues. They reveal which formation histories are more compatible with a measurement, but they rarely reduce billions of years of galactic evolution to one certain birthplace or moment. That connection is not a universal stopwatch. The Milky Way is not chemically uniform. Ratios vary with distance from the galactic center, local star formation history, mixing, and the material inherited by a forming system. A ratio measured in one object cannot be converted directly into one age without considering where and how its source environment evolved. Still, the direction of the evidence was meaningful. 3I/Atlas combined an extreme water DH ratio with high carbon isotope ratios and an unusual nitrogen ratio. The water favored very cold chemistry. The carbon and nitrogen favored material shaped in a relatively less enriched environment. Together, they described a source unlike the region and period that produced the solar system. This is why the carbon evidence reached beyond the idea of a cold outer disk. Cold outer disks can form around young stars today, but their raw material comes from the present chemical state of the galaxy. A cold disk billions of years ago would begin with a different mixture because fewer generations of stellar processing had contributed to its gas. The isotope ratios offered a possible way to distinguish those histories. The ratios also had to be separated from assumptions about quality or complexity. A less enriched environment is not an inferior one. It is simply an earlier or differently located chemical environment. Planetary building blocks can form from such material. Indeed, the existence of an icy planetesimal carrying carbon, nitrogen, oxygen, and organic compounds shows that complex solid material could assemble under conditions unlike those surrounding the birth of the Sun. Nor did the isotope evidence mean that astronomers could identify the comet's parent star. Many stars may share broadly similar chemical conditions. Galactic mixing blurs boundaries, and billions of years of motion erase a unique trail. The ratios constrain a class of environments. They do not provide an address. At this point, 3 evidence layers could be kept distinct. The spectra directly measured features associated with specific isotopes. Chemical interpretation connected those ratios to cold formation and relative enrichment. Galactic models would then be needed to connect the enrichment pattern to a likely period of formation. Each layer depended on the one below it, and each introduced new uncertainty. The direct measurements were the strongest layer. The formation environment was a scientific inference supported by known isotope chemistry. The age would be a model-dependent conclusion. Keeping these layers separate prevents a possible age from being presented as if a telescope had observed the comet being born. The provisional answer was therefore careful but powerful. 3I/Atlas contained unusually little carbon-13 relative to carbon-12, with compatible high ratios measured in carbon dioxide, carbon monoxide, and CN. Its nitrogen ratio strengthened the picture of a chemically distinct source. The combined pattern was consistent with formation in a cold, relatively metal-poor environment that had experienced less stellar enrichment than the material around us. Yet even this evidence left an important limitation. A chemical environment is not a calendar date. High carbon ratios may reflect age, galactic location, local history, or some combination of them. To estimate when the comet formed, researchers had to compare its measured composition with models of how isotope ratios changed across the Milky Way. Before making that translation, the physical setting itself needed to be reconstructed. How could extremely cold, relatively unprocessed material move from a molecular environment into a solid planetesimal, survive later heating, escape its star, and preserve its isotope pattern across interstellar time. The ratios had supplied the ingredients of a birthplace. The next step was to rebuild the lost freezer in which those ingredients became a comet. The isotope ratios did not provide a photograph of the comet's birthplace. They provided constraints. Any plausible environment had to explain water strongly enriched in deuterium, carbon relatively poor in carbon-13, nitrogen that followed the same broad chemical difference, and ice that survived without losing those signals. Reconstructing the birthplace meant finding a physical sequence capable of producing all of them together. The first requirement was extreme cold. Temperatures no higher than about 30 Kelvin are far below the freezing point of water. 30 Kelvin is close to minus 243 degrees Celsius. At that temperature, many substances that exist as gases in warmer regions can freeze onto tiny grains of dust. The grains become coated with layers of ice containing water and carbon-bearing material. Their surfaces provide places where atoms and simple molecules can meet, react, and remain stored. Cold also changes the balance of isotope chemistry. Reactions that enrich molecules in deuterium become more effective, and the resulting compounds can be preserved in ice. The high DH ratio in 3I/Atlas therefore points toward material that spent important stages of its history in such a frigid setting. The evidence does not demand that every grain experienced one identical temperature, but it favors a source dominated by very cold chemistry. There are two connected environments in which this history could begin. One is a cold, dense region of a molecular cloud before or during star formation. The other is the distant outer part of the disk that forms around a young star. Material can pass from the cloud into the disk, carrying some chemical signatures with it, and then undergo further processing before becoming part of a planetesimal. A protoplanetary disk is made of gas and dust orbiting a young star. Close to the star, temperatures are high enough to vaporize many ices. Farther away, the disk becomes colder. Different substances freeze at different distances and under different conditions. In the outer disk, water, carbon dioxide, carbon monoxide, methane, and other volatiles can become available as solid material or remain locked onto grains. This provides a broad physical home for the chemistry of 3I/Atlas. The comet likely assembled from material in a cold outer region, rather than near the warm zone where rocky planets form. Its volatile inventory and isotope ratios are consistent with grains that carried both inherited cloud chemistry and disk chemistry. The exact division between those sources cannot be recovered, but the final mixture preserved the signature of low-temperature processing. The path from microscopic grain to comet required growth across many scales. Dust grains coated with ice collided and sometimes stuck together. Larger aggregates formed from smaller ones. Continued accumulation produced solid bodies large enough to behave as planetesimals, the building blocks from which planets, moons, asteroids, and comets emerge. This description is a general formation mechanism, not a recovered film of one unique event. Astronomers did not observe 3I/Atlas assembling. They infer that it is an icy planetesimal because of its natural cometary activity, composition, and physical behavior. The isotope evidence constrains the material involved, while established planet formation processes provide a plausible route for turning that material into a solid body. Preservation is as important as formation. If the ice had moved repeatedly through warm regions, evaporated, mixed completely, and condensed under different conditions, its isotope ratios could have changed. The survival of extreme deuterium enrichment suggests that the relevant material avoided enough thermal reprocessing to retain a cold signature. That does not mean the comet remained untouched. It may have experienced radiation, collisions, surface alteration, and periods of warming over its history. Its outermost layers may differ from material farther inside. The point is not perfect preservation. It is that later events did not erase the broad isotope pattern eventually measured in the coma. The carbon evidence adds another constraint to this freezer. Cold alone cannot explain why carbon-13 was relatively scarce. A modern outer disk could also reach very low temperatures. The source material for 3I/Atlas appears to have come from a relatively less enriched galactic environment. The freezer was therefore not only distant from a star's heat, it was built from a chemical mixture different from the mixture that formed the solar system. Once the planetesimal existed, it somehow had to leave its star. Planetary systems do not keep every object they create. During formation, growing planets exchange energy and momentum with smaller bodies. A close gravitational encounter can alter a planetesimal's orbit. Repeated encounters may send it inward, move it outward, or accelerate it beyond the system's escape speed. Interactions between stars or changes within a crowded young environment can also disturb distant material. For 3I/Atlas, ejection is a strong general inference because the comet arrived from interstellar space and must once have become unbound from whatever environment produced it. But the exact mechanism is unknown. No evidence identifies a particular planet, stellar encounter, or date. Any detailed account of one decisive gravitational event would be an invented biography rather than a scientific reconstruction. The timing of ejection is equally uncertain. The comet might have been expelled early while planets were still forming, or later after the system evolved. If it formed 10 to 12 billion years ago, that does not automatically mean it spent the entire interval traveling alone. Formation age and interstellar travel time are separate quantities. After ejection, the comet entered the space between stars. There, sunlight from its parent system faded. Its most volatile surface material may have changed, but deep ice could remain cold. Across galactic time, the object would pass through changing radiation environments and weak gravitational influences. Its trajectory would be gradually altered, making the path back to one star impossible to reconstruct after billions of years. Eventually, its motion brought it into the region controlled by the Sun. The comet was already moving through the galaxy, and its path happened to cross our neighborhood. Solar gravity bent and accelerated the trajectory during the encounter, while solar heat reopened the chemical archive stored within the nucleus. The resulting story can now be divided by confidence. Direct observation established the hyperbolic orbit, cometary activity, released molecules, and isotope ratios. Strong inference connected the isotope pattern with a very cold, relatively metal-poor formation environment, and limited later thermal reprocessing. A plausible physical model placed that material in a distant disk, where icy grains accumulated into a planetesimal. Another strong general inference required ejection from its original system. The identity of the star, the disturbing planet, the ejection date, and the precise journey remain unknown. This hierarchy prevents a smooth narrative from becoming false certainty. It is possible to describe how such a comet can form and escape without claiming that every step happened in one particular way. The reconstruction is valuable because several independent clues point toward the same class of environment, not because science has recovered a lost scene. The freezer also clarifies what the word ancient could mean. The ice may include chemistry inherited from material that existed before the comet assembled. The solid planetesimal has a formation time, while some atoms and molecules are older still. When researchers estimate an age for 3I/Atlas, they are trying to identify the likely epoch when this material accreted into the object, not the age of every atom inside it. That distinction will matter when the possible 10 to 12 billion year range appears. Carbon, oxygen, and hydrogen themselves existed before the comet. Cold grains may have carried earlier chemical memories. The modeled age refers to the formation of a planetary building block within an evolving galactic environment. The physical reconstruction therefore delivered another local answer. 3I/Atlas most likely formed as an icy outer system planetesimal from extremely cold and relatively less enriched material. It preserved enough of that chemistry to carry the record through ejection and interstellar travel. Nothing in the evidence requires an artificial origin, a dangerous purpose, or an impossible substance. But the freezer still had no date written on its walls. To place it in time, astronomers needed to compare the measured carbon ratios with the changing chemical history of the Milky Way. That required a model broad enough to connect one comet's molecules with generations of stars. The investigation had moved from an orbit to a coma, from a coma to atoms, and from atoms to a lost formation environment. It was now ready for its largest change of scale, dating a comet with the history of the galaxy. Dating a comet with the history of the galaxy requires a different kind of clock. There is no ring to count, no written record, and no direct view of the moment when microscopic grains became a solid body. Instead, researchers compare the comet's chemical pattern with models describing how the Milky Way changed as generations of stars formed and died. The starting point is measured, not imagined. Spectra of 3I/Atlas showed high carbon-12 to carbon-13 ratios in carbon dioxide, carbon monoxide, and CN. They also showed an extreme enrichment of deuterium in water and an unusual nitrogen ratio. These observations established the input. The model entered only when researchers asked which galactic environments and periods were most compatible with that combination. Galactic chemical evolution models attempt to follow the changing composition of gas across time. They include the formation of stars, the elements and isotopes produced by different stellar populations, the material returned when stars lose mass or die, and the mixing of that material into later generations. The models can then estimate how ratios such as carbon-12 to carbon-13 may differ between epochs and locations. The basic direction is intuitive even when the details are complex. Early gas had experienced fewer cycles of stellar processing. Later gas contained the accumulated products of more stars. Because carbon-12 and carbon-13 are not contributed in the same proportions or on identical schedules, their ratio changes as the galaxy evolves. A source with relatively little carbon-13 can therefore be more compatible with an earlier, less enriched environment. But the model cannot simply take one measured ratio and print a birthday. The Milky Way has a structure. Its inner and outer regions evolve differently. Star formation does not proceed at the same rate everywhere. Gas moves and mixes. A chemical pattern may reflect both time and location. Researchers must consider a range of formation histories rather than a single universal chemical timeline. When the measured carbon ratios of 3I/Atlas were interpreted through those models, the preferred formation epoch was roughly 10 to 12 billion years ago. This was an estimate of when the material may have accreted into a planetesimal under the inferred early galaxy conditions. It was not a direct measurement of elapsed time, and it was not a claim that every atom inside the comet formed then. The scale of the estimate becomes clearer through comparison. The solar system formed about 4.5 to 4.6 billion years ago. If 3I/Atlas accreted 10 to 12 billion years ago, it could be more than twice as old as the Sun and planets. Earth would not merely be younger by a small fraction of cosmic history. It would have appeared billions of years after this comet had already become a solid remnant of another system. The universe itself is about 13.8 billion years old. A formation age of 10 to 12 billion years would therefore place the comet's birth when the universe was already roughly 1.8 to 3.8 billion years into its history. This is ancient, but it is not immediately after the Big Bang. Stars had already formed, processed material, and created the carbon and oxygen needed for ice and solid planetary bodies. That period overlaps broadly with the era often called cosmic noon. The name refers to the time when star formation across the universe was near its peak. Galaxies were producing stars at rates much higher than those common today. Cosmic noon was not the dawn of everything. It was a busy middle chapter in which many stellar systems were appearing while the chemical enrichment of galaxies was still developing. Placing 3I/Atlas near this period changes the meaning of its ordinary materials. Water ice, carbon compounds, dust, and organic chemistry were not waiting for the solar system. Planetary building blocks could assemble during an era when the universe was forming stars intensely and the Milky Way was chemically younger. The comet may preserve one physical example of that early activity. The evidence does not show what kind of planets surrounded its parent star. It does not show that life emerged, that a civilization existed, or even that the system retained mature planets. The justified implication is narrower. An icy planetesimal could form from cold, relatively less enriched material billions of years before the Sun. That alone extends the known diversity of planetary construction across galactic time. Why favor 10 to 12 billion years rather than merely saying older than the solar system? The specific range comes from comparing measured isotope ratios with the predicted chemical evolution of the galaxy. High carbon-12 to carbon-13 ratios indicate limited carbon-13 enrichment. The model asks when and where source material with that pattern was likely to be available. The water DH result supports an extremely cold formation environment, strengthening the picture of preserved early material rather than heavily reprocessed local-style ice. The age inference is therefore cumulative. The orbit establishes that the object came from another system. The coma supplies material for spectroscopy. The spectra provide isotope ratios. Chemistry links those ratios to temperature and enrichment. Galactic models connect enrichment with possible epochs. Removing any link weakens what comes after it. This chain also reveals why the age should be described as possible or preferred, not proven. Every model simplifies a galaxy too complex to reproduce perfectly. Stellar yields must be estimated. Mixing must be represented. The birth radius of the comet's system is unknown. The material may have moved before it entered a protoplanetary disk. Chemical reactions inside the disk may have altered inherited ratios. The measured ranges themselves have uncertainty. Carbon dioxide gave a broad carbon ratio from roughly 141 to 191, while carbon monoxide produced about 123 to 172. CN yielded a value around 151. These results agree in their general direction, but they do not specify one exact ratio without error. Feeding a range into a model naturally produces a range of compatible histories. There is also a difference between the age of source material and the age of the assembled comet. Atoms were created before the planetesimal existed. Icy grains may have spent time in a molecular cloud. Accretion may have occurred after the parent star began forming. The estimate concerns a likely accretion epoch, but the boundary between inherited chemistry and disk processing introduces uncertainty. Galactic location presents another challenge. The ratio between carbon isotopes can vary across the Milky Way. Material formed far from the galactic center may resemble material from a different time elsewhere. Without a recovered natal star, researchers cannot know the precise chemical history of the region that produced the comet. The model must consider likely environments rather than one known address. These limitations do not make the estimate meaningless. A scientific model earns value by testing which histories can reproduce observations and by exposing the assumptions on which its answer depends. The 10 to 12 billion year range is a disciplined interpretation of a rare chemical pattern. It is stronger than a guess, but less direct than radiometric dating of a sample in a laboratory. The distinction can be stated plainly. Astronomers measured the orbit and isotope ratios. They inferred very cold, relatively metal-poor formation conditions. Under current galactic chemical evolution models, those conditions favor accretion roughly 10 to 12 billion years ago. Confidence is high in the object's interstellar origin and unusual chemistry, strong in its cold formation, and more moderate in the exact age. This layered confidence protects the discovery from two opposite mistakes. One mistake is exaggeration, declaring that 3I/Atlas is certainly 12 billion years old and older than nearly every object in existence. The other is dismissal, claiming that model dependence means nothing can be learned. The evidence supports an ancient origin while leaving room for revision. The title's phrase, "older than almost everything," must therefore be narrowed. The comet is not older than the universe. It is not older than the earliest stars, and it may not be older than every ancient solid body. Many stars and some planetary systems existed before the proposed formation epoch. The defensible claim is that 3I/Atlas may be among the oldest solid planetesimal fragments chemically studied from another planetary system. That formulation loses none of the real scale. A natural object that may have become solid before the Sun existed by 5 to 7 billion years passed through our system and released measurable gas. Its chemistry connected instruments operating in the present with planetary formation near the period of peak cosmic star production. The age model also raised a wider question. If one of the first three known interstellar objects carries such ancient chemistry, how common are similar fragments? Perhaps the galaxy contains enormous numbers of old planetesimals thrown out by vanished systems. Perhaps 3I/Atlas is unusual and detectable precisely because its activity made it visible. With a sample of 3, the population cannot be known. Independent clues could at least test whether the ancient interpretation was coherent. The comet's high velocity was compatible with older stellar populations associated with the galaxy's thick disk. That did not measure its age, but it offered a separate line of consistency. Comparisons with solar system comets, 1I/Oumuamua and 2I Borisov, could reveal how exceptional its chemistry appeared. The galactic clock had produced the documentary's most dramatic provisional answer. 3I/Atlas may have accreted 10 to 12 billion years ago, during the broad era of cosmic noon. Yet a claim of that size could not stand on one model alone. It had to survive comparison, independent checks, selection effects, and the severe limits of a three-object sample. The investigation had finally reached an age. The next question was whether anything else in the evidence supported it. An age estimate drawn from galactic chemistry becomes more persuasive when independent evidence points in the same direction. It does not need every clue to produce the same number. In fact, independent clues are valuable because they measure different parts of the problem. The question was whether the orbit, velocity, and comparisons with other comets made the ancient interpretation more coherent or exposed a contradiction. The first comparison was with comets born around the Sun. Solar system comets do not share one perfect composition. They formed in different regions, experienced different histories, and display a range of volatile abundances and isotope ratios. Any comparison that treats them as chemically identical would create a false baseline. Yet their measured values still define the local population against which an interstellar visitor can be judged. Against that population, the water in 3I/Atlas was extreme. Its DH ratio of 0.98% was roughly 30 times the representative mean cited for solar system comets. The carbon ratios were also much higher than the commonly used solar system value, near 90. These contrasts did not merely place the object at one edge of a familiar range. They identified a combination of isotope signatures, unlike the local cometary material normally sampled. The comparison does not prove age. A chemical outlier could reflect an unusual region or pathway rather than an ancient epoch. But it rules out the simplest explanation, that 3I/Atlas was chemically interchangeable with a typical solar system comet. Its interstellar origin was dynamic, and its difference was chemical as well. The next comparison involved the only two confirmed interstellar objects that came before it. 1I/Oumuamua was discovered in 2017 after it had already passed closest to the Sun. It moved on an interstellar trajectory, but it did not develop the bright, conventional coma that would have provided an extensive sample of gas. Astronomers had to work with a brief observing window and limited chemical information. Its unusual properties created a long debate, but they did not yield the isotope inventory needed for the kind of formation history reconstructed for 3I/Atlas. 2I Dap Borisov, discovered in 2019, was clearly active and cometary. Its coma allowed direct chemical study, making it a more natural comparison for 3I/Atlas. Borisov demonstrated that an object from another planetary system could resemble a recognizable comet while carrying its own compositional pattern. Yet its measured chemistry did not display the same complete set of extreme isotope signatures later found in 3I/Atlas. The progression from 1I to 2I to 3I was therefore not a simple ranking from less strange to more strange. Each object was discovered under different circumstances and offered different evidence. 1I provided a difficult, largely inactive target. 2I provided an active comet. 3I provided a highly active object observed with enough instruments and spectral detail to reveal exceptional water, carbon, and nitrogen isotopes. This difference in available evidence matters. An object may lack a reported isotope anomaly because the relevant measurement was impossible, not because its material was ordinary. The first three visitors cannot be placed on one complete chemical chart when many cells remain empty. Comparing them requires distinguishing absence of evidence from evidence of absence. Even so, 3I/Atlas expanded the known range. Before it, no confirmed interstellar visitor had supplied this combination of isotope measurements. Its chemistry showed that planetary debris moving through the galaxy can preserve conditions far outside the familiar local comet patterns. Motion offered another check. 3I/Atlas had a hyperbolic excess velocity near 58 kilometers per second, faster than the earlier confirmed interstellar visitors. In the Milky Way, stellar populations with different ages can have different patterns of motion. Older populations have experienced more time for gravitational interactions to alter and spread their velocities. The galaxy's thick disk population is generally associated with older stars and distinct kinematics. The speed of 3I/Atlas was compatible with an origin connected to such an older population. This did not mean astronomers could read an age directly from velocity. In isolation, without its parent star, those contributions cannot be separated completely. Kinematics therefore served as a consistency check, not a second clock. The isotope models suggested ancient formation. The high speed did not contradict that interpretation and was broadly compatible with old stellar populations. If the comet had moved in a way strongly associated with a young, known nearby system, the ancient interpretation might have faced tension. Instead, its motion left the old origin scenario open. The distinction between support and proof must remain clear. Two uncertain clues do not become certain merely because they agree. Their assumptions may overlap, or the agreement may cover a broad range. But evidence from chemistry and motion responds to different physical histories. Compatibility between them is more informative than repeating one chemical analysis twice. The comparison also exposed a severe problem: selection effects. Astronomers do not detect every object passing through the solar system. A visitor must be bright enough, close enough, or active enough to rise above survey limits. An icy body that develops a large coma can be found at a greater distance than a small, dark, inactive rock. Discovery conditions therefore shape the sample before scientific analysis begins. 3I/Atlas may have been detected partly because solar heating made it active and visible. That does not make its chemistry less real, but it means the first three interstellar objects are not necessarily a fair miniature of the full population. They are the objects that happened to cross observable paths while surveys were capable of finding them. Timing adds another bias. Modern sky surveys have operated with sufficient sensitivity for only a short period compared with galactic time. The fact that three objects were confirmed within less than a decade does not by itself reveal how many exist, because detection methods were changing and the search interval was brief. Population estimates require assumptions that this small sample cannot test securely. The sample also contains three very different observing opportunities. 1I was recognized late and lacked a conventional coma. 2I was active. 3I was observed across a coordinated campaign and yielded unusually detailed spectra. Any claim that ancient, deuterium-rich comets are common or rare would depend on data that do not yet exist. This limit changes the scientific consequence. 3I/Atlas proves that at least one observed interstellar planetesimal carried this chemical pattern. It does not prove that most interstellar comets are ancient. It cannot show whether the Milky Way is filled mainly with early relics, younger fragments, or a broad mixture of both. Future detections could transform the interpretation. If many interstellar comets show high DH and high carbon ratios, 3I/Atlas may become the first clear member of a large ancient population. If later objects look chemically closer to solar system comets, it may remain an extreme outlier. Every new visitor will test whether the current story describes one comet or a common galactic process. For now, the comparisons support a calibrated conclusion. Relative to measured solar system comets, 3I/Atlas is chemically exceptional. Relative to 1I and 2I, it provides a richer isotope record rather than a simple measure of greater strangeness. Its high velocity is compatible with old stellar populations, but it does not independently establish age. The total sample remains too small for population claims. This mixture of convergence and limitation is scientifically productive. The ancient origin model survives the available checks. Nothing in the comparisons requires a young local-style comet, and the kinematics broadly fit an old source. Yet the evidence cannot tell whether 3I/Atlas is typical of debris formed near cosmic noon or a rare survivor selected by chance. The larger mystery had therefore changed. The question was no longer whether the comet could be ancient. The evidence allowed that possibility. The question was how much of its individual history could ever be recovered, and how confidently the modeled age could be attached to one unnamed object. Comparison had carried the investigation as far as the existing sample allowed. Before the title could receive its final answer, every remaining boundary had to be made explicit. What was measured? What was inferred? What depended on models? And what the galaxy had erased beyond recovery? Every strong scientific story needs a boundary. Without one, evidence becomes a biography more detailed than the observations can support. For 3I/Atlas, the measurements reveal an extraordinary amount, but they do not recover a complete journey. The final answer depends on knowing exactly where certainty ends. The first level is direct observation. Astronomers measured positions of the comet against the sky and used them to calculate its trajectory. They observed a deeply hyperbolic orbit and an excess velocity that remained after solar gravity was accounted for. They recorded cometary activity, imaged the coma and tails, and collected spectra containing features associated with water, carbon dioxide, carbon monoxide, CN, and other material. They measured isotope ratios with stated uncertainties. These observations are the firm foundation. They may be refined as analyses improve, but they are not philosophical interpretations. The orbit is data constrained by repeated positions. The spectral features are light collected by instruments. The numerical ratios come from analyzing that light through established physical methods. The second level is strong scientific inference. No telescope photographed the ice forming below 30 Kelvin. Instead, researchers used known isotope chemistry to connect extreme deuterium enrichment with very cold conditions. They used the relative scarcity of carbon-13 and the nitrogen result to infer formation from relatively less enriched material. They concluded that the isotope pattern had survived limited thermal reprocessing because extensive warming and chemical exchange could have altered it. These conclusions are more interpretive than the measurements, but they are not free speculation. They are constrained by how isotopes behave and by agreement across several molecules and instruments. A different explanation would still have to reproduce the same water, carbon, and nitrogen evidence. The third level is model-dependent conclusion. The possible formation age of 10 to 12 billion years belongs here. Galactic chemical evolution models translate the isotope pattern into a range of compatible epochs and environments. The age is meaningful because the models connect measured ratios with the accumulated effects of stellar generations. It remains conditional because the birth location, local mixing history, and exact balance between inherited and disk chemistry are unknown. The safest wording is not, "The comet is 12 billion years old." It is that current models favor a possible accretion age of roughly 10 to 12 billion years. That statement preserves the discovery while acknowledging the machinery used to reach it. The fourth level is plausible but unrecovered history. 3I/Atlas must have escaped the system in which it formed. Gravitational encounters with growing planets provide a natural general mechanism for ejecting planetesimals. A stellar encounter could also disturb distant material. Yet no evidence identifies the responsible planet, star, encounter, or moment. A narration that describes one specific ejection scene would cross from explanation into invention. The travel time is also unknown. If the comet formed 10 billion years ago, it may not have entered interstellar space immediately. It could have remained in its parent system for an interval before ejection. Formation age and wandering time cannot be treated as equal. The parent star cannot be recovered from the present orbit with confidence. Over short times, astronomers can calculate motion backward and compare it with nearby stars. Over immense periods, tiny uncertainties expand. Stars move through the galaxy. Molecular clouds exert gravity, and repeated disturbances gradually alter trajectories. After billions of years, many possible paths become compatible with the present state. This is not merely a shortage of computer power. A calculation cannot restore information that measurements no longer contain with sufficient precision. If a tiny uncertainty grows across thousands of encounters and millions of orbital motions, the final range can spread across enormous regions. The galaxy has effectively erased the return address. The nucleus creates a more immediate uncertainty. Because the coma surrounded and brightened the object, the solid body could not be measured as a clean disk. Estimates therefore ranged from hundreds of meters to several kilometers. This affects questions about mass and activity, but it does not weaken the interstellar orbit or isotope measurements. Population claims have an even wider boundary. Only 3 interstellar objects have been confirmed. They were discovered under different circumstances and did not provide equal data. From this sample, science cannot determine how many interstellar planetesimals are ancient, how many resemble solar system comets, or whether 3I/Atlas represents a common class. The fifth level is philosophical reflection. The possibility that the comet came from a vanished planetary system can inspire ideas about lost worlds, the lateness of Earth, and the scale of cosmic history. Those reflections can be meaningful, but they are not additional measurements. The chemistry does not prove that inhabited planets existed beside the comet. It does not show what happened to its star or whether any planets survived. Separating these 5 levels protects the investigation from 2 forms of false certainty. The first turns every inference into direct fact. The second treats every unknown as permission to insert any possibility, including artificial origin or hidden danger. Neither approach respects the evidence. Honesty about these limits makes the surviving conclusions stronger, because every remaining claim has passed through an evidential filter. Uncertainty is not an empty space where all explanations become equal. The comet's natural activity, molecular inventory, orbit, and isotope chemistry strongly restrict what can reasonably be claimed. There is no positive evidence of technology. There was no impact trajectory. An unknown parent star does not make an artificial explanation as likely as natural planetesimal formation. At the same time, confidence in natural origin does not produce confidence in every detail. Science can know the class of object without knowing its unique life story. It can constrain formation conditions without naming a star. It can favor an ancient epoch without supplying a precise birthday. The evidence hierarchy can therefore be stated in one continuous chain. It is observed that 3I/Atlas is active, chemically measurable, and dynamically interstellar. It is strongly inferred that its material formed under extreme cold in a relatively less enriched environment. It is modeled that accretion may have occurred 10 to 12 billion years ago. It is plausible that gravitational interactions ejected it. It is unknown where, when, and by what exact encounter that happened. Each level answers a different question. Confusion begins when one answer is asked to do the work of another. The orbit proves origin outside the solar system, not age. Water date supports cold chemistry, not a calendar date. Carbon ratios support an early or differently located environment, not one address. Galactic models estimate an epoch, not an eyewitness history. With those limits established, uncertainty no longer weakens the title answer. It calibrates it. The comet does not need to be exactly 12 billion years old to be extraordinary. Even the lower part of the favored range would place its formation billions of years before the Sun. The central result survives the loss of a precise biography. The remaining question can now be answered directly. How old is 3I/Atlas according to the strongest available evidence? What does older than almost everything exaggerate? And what is genuinely unsettling about a harmless natural comet? The measurements, inferences, models, and unknowns are finally in their proper places. The investigation is ready for its scientific conclusion. The answer can now be stated without turning possibility into certainty. 3I/Atlas is a natural interstellar comet whose measured chemistry is consistent with formation in an exceptionally cold, relatively less enriched environment. When its carbon isotope ratios are interpreted through current models of galactic chemical evolution, they favor a possible accretion age of roughly 10 to 12 billion years. That would make the comet more than twice as old as the solar system and place its formation billions of years before Earth existed. The age is not a direct measurement. It is the end of an evidence chain. The first link is the orbit. Repeated observations showed a deeply hyperbolic path with an eccentricity near 6.14 and a hyperbolic excess velocity around 58 kilometers per second. The comet arrived with enough motion to escape the Sun after its passage. Its trajectory was not created by a planet during the encounter, and it will not return. This establishes with high confidence that the object came from outside the solar system. The orbit also removed the false danger. 3I/Atlas remained about 1.8 astronomical units from Earth at its closest. It never occupied an impact trajectory. Its speed made it scientifically remarkable, not physically threatening to our planet. The second link is its activity. Solar heating released gas and dust from a hidden icy nucleus, producing a coma that telescopes could study. That activity was natural cometary behavior. The object contained water, carbon dioxide, carbon monoxide, methane, carbon and nitrogen-bearing material, organics, dust, and nickel. None of these substances required technology or biology. The third link is water. Webb measured a deuterium to hydrogen ratio of 0.98%, with an uncertainty of 0.06%. That was roughly 30 times the representative mean used for solar system comets, and far above Earth's ocean value. ALMA provided independent evidence of strongly deuterated water. Known isotope chemistry connects such enrichment with extremely cold conditions and limited later thermal reprocessing. The fourth link is carbon and nitrogen. Carbon dioxide showed a carbon-12 to carbon-13 ratio between roughly 141 and 191. Carbon monoxide produced about 123 to 172. CN observed with the Very Large Telescope gave a compatible value around 151, while nitrogen-14 to nitrogen-15 was around 363. Different molecules, instruments, and wavelengths converged on a chemically unusual source. High carbon ratios mean carbon-13 was relatively scarce. In the context of stellar recycling, that pattern is consistent with material that had experienced less enrichment from successive generations of stars. Combined with the water evidence, it points toward a cold environment built from a different galactic mixture than the one that produced the solar system. The fifth link is the model. Galactic chemical evolution connects isotope patterns with the changing composition of the Milky Way. Under current versions of those models, the measured carbon ratios favor a formation epoch roughly 10 to 12 billion years ago. The comet may therefore have accreted during the broad era of cosmic noon, when star formation across the universe was near its peak. The final supporting clue is motion. The high velocity of 3I/Atlas is broadly compatible with older stellar populations associated with the galaxy's thick disk. Velocity cannot provide an independent birthday, and ejection adds its own motion. Still, the kinematics do not conflict with the ancient chemical interpretation. This is the cumulative case. Orbit proves foreign origin. Activity exposes material. Isotopes constrain formation conditions. Galactic models connect those conditions with a likely epoch. Kinematics provide consistency. No single clue carries the entire conclusion. How old, then, is 3I/Atlas? The strongest answer is that it may have formed about 10 to 12 billion years ago. Confidence in the exact range is moderate because it depends on models, an unknown birth location, and uncertain chemical processing. Confidence that the object is interstellar is high. Confidence that its ice records extremely cold and chemically distinct conditions is also strong. The difference between those confidence levels is part of the result, not a weakness to hide. Future models may move the favored age. Additional observations may refine the ratios. New interstellar comets may reveal whether 3I/Atlas represents an ancient population or an extreme case. But any revision will begin from the unusual measurements already made. That calibration matters because a qualified discovery can remain profound. The evidence does not become smaller when its boundaries are stated. It becomes clearer, durable, and more useful to whatever future observations reveal. Is it older than almost everything? No, not literally. The universe is about 13.8 billion years old. The earliest stars formed before the possible accretion of this comet. Many old stars, stellar remnants, and ancient materials may predate it. Some planetary systems could also have formed earlier. Older than almost everything is a dramatic compression, not a defensible scientific category. The accurate claim remains extraordinary. 3I/Atlas may be among the oldest solid planetesimal fragments chemically studied from another planetary system. It could have become a coherent, icy body 5 to 7 billion years before the Sun formed. By the time Earth began assembling, this comet may already have possessed a history longer than the entire age of our planet today. That comparison must not be confused with the age of its atoms. Hydrogen is far older than the comet. Carbon and oxygen were produced before the planetesimal assembled. Some ice chemistry may have been inherited from a molecular cloud. The 10 to 12 billion year estimate concerns the likely accretion epoch of the planetary building block, not the creation of every particle inside it. Was it terrifying? Not as a collision threat, not as an alien machine, not because its organic compounds imply life. The evidence supports none of those ideas. The comet behaved as a natural icy body, and its path kept it safely away. The unsettling part is what its natural history implies. If the age model is broadly correct, planetesimals were forming under early Milky Way conditions long before the solar system existed. Around an unknown star, cold grains gathered into a solid body while the wider universe was near its peak period of star formation. A planetary system may have taken shape around that star, scattered some of its building material, and eventually disappeared from any recoverable connection with the comet. The evidence does not show whether that system contained Earth-like planets. It does not reveal life, oceans, or observers. Those would be inventions. What it shows is more restrained. The physical process of building icy planetary material was already operating billions of years before our own system began. This removes humanity from the beginning of the planetary story. The sun did not appear at the first moment when matter learned to build worlds. Earth formed late enough that an object from another system may already have spent several billion years existing before our planet had a surface. The comet also shows how much history can vanish. Its parent star has no recoverable identity. The date and mechanism of ejection are unknown. Any planets that shared its system remain beyond observation. The only surviving connection is chemical, ratios preserved in water, carbon, and nitrogen, released during a brief passage near a star that was not its own. This is a different kind of unease from fear. Physical danger has a direction and a time. It can approach, pass, or be avoided. Deep time offers no such target. It reveals that entire planetary histories can occur before ours, leave fragments, and become unreadable except for a few atomic patterns. 3I/Atlas therefore does not warn that something is coming. It demonstrates how much has already happened. The title can now be corrected and fulfilled at the same time. The comet is not proven to be older than almost everything, but current evidence makes a 10 to 12 billion year origin scientifically plausible. It is not terrifying because it threatened Earth, but because a harmless piece of ice may embody a planetary past older than the Sun by billions of years. That conclusion remains calibrated. The spectra are measurements. The cold origin is a strong inference. The age is model-dependent. The lost planetary history is a reasonable implication, while any story about specific worlds remains unknown. Nothing must be exaggerated for the scale to remain immense. There is also a consequence for future science. With only 3 confirmed interstellar objects, 3I/Atlas cannot define the population. If future visitors carry similar isotope patterns, the galaxy may contain a large reservoir of ancient planetary debris. If they differ, this comet may stand as a rare chemical survivor. Either result would reveal more about how planet formation changed across galactic history. For now, the scientific climax belongs to one small object. It arrived on an orbit the Sun could not close. It released ordinary molecules carrying extraordinary ratios. Those ratios reconstructed extreme cold and limited enrichment. A galactic model then placed its possible formation near cosmic noon. The final answer is neither certainty nor dismissal. 3I/Atlas is securely interstellar, naturally cometary, chemically exceptional, and plausibly 10 to 12 billion years old. Its exact birthday and birthplace remain beyond reach. What remains is not another scientific theory. It is the change in perspective created by the answer. At the beginning, 3I/Atlas was a moving point of light that seemed alarming because it came from outside. Now its meaning lies in the opposite fact. It was small, distant, and harmless, yet it carried evidence from a history vastly older than our own. The investigation has answered what the comet may be. One final question remains. What does it mean for a young planetary system like ours to briefly encounter a fragment whose home, path, and companions have been erased by time? The point of light is leaving now. It will grow fainter as distance increases and sunlight weakens. The gases that made it visible will diminish. Its coma will thin, and the ice below the surface will return to darkness. The sun will continue slowing the comet for a time, but it cannot call it back. 3I/Atlas will pass beyond the planets and resume a journey with no known destination. Nothing about that departure is unusual for an interstellar object. It arrived, crossed the sun's domain, and escaped. What changed was our understanding of what the small body may contain. Before its passage, the comet was unknown to humanity. Its parent star was already lost from its history. If its modeled age is broadly correct, the object may have existed for billions of years before the sun formed, carrying ice assembled from a colder and less enriched Milky Way. It traveled without a name until a survey recognized its motion against the sky. For a brief interval, one planetary system was able to examine material made in another. For those few months, the boundary between our system and another was not a vast abstraction. It was gas expanding around one visible body, carrying evidence older than every human memory, every civilization, and the planet beneath the living observers themselves. The connection did not require a message, a machine, or an intended journey. Solar heat released molecules. Telescopes separated their light. The relative forms of hydrogen, carbon, and nitrogen preserved information that no map could provide. Chemistry became the only surviving link between this comet and a birthplace that cannot be recovered. That link is incomplete, but incompleteness gives it meaning. We do not know the star that warmed the comet first. We do not know what other bodies formed beside it, how long the system endured, or which event finally sent this fragment away. The evidence cannot turn those unknowns into a story. It can tell us something quieter. Our solar system belongs to a history that began long before it. By the time the sun gathered from its own cloud, other stars had already lived and died. Other disks had assembled dust and ice. Other planetesimals had formed, collided, scattered, and escaped. Earth did not appear at the opening of planetary history. It emerged after the galaxy had already spent billions of years building and losing worlds. This does not make our planet unimportant. It changes the scale on which importance is understood. Earth is not meaningful because it came first. It is meaningful because, during one brief period, matter here became capable of reading the history carried by matter from somewhere else. The instruments that observed 3I/Atlas did not restore its past. They recovered fragments of evidence, an orbit that would not close, water enriched in deuterium, carbon with an unusual isotope balance, and chemistry consistent with extreme cold. From those fragments, science built a careful range of possibilities and marked the places where knowledge stopped. That restraint is part of the achievement. A lost history does not need to be completed with invention. The measured pieces are enough to reveal that planetary formation is older, broader, and more varied than the experience of one solar system. Somewhere in the comet's past, ordinary matter became ice around an unknown star. Gravity gathered grains into a small world. Later, gravity released it. The details are gone, but the physical consequence survived. A fragment crossed the galaxy and entered the reach of observers who could recognize the atomic differences hidden inside its water and carbon. The encounter lasted only a moment compared with the age being investigated. Human astronomy had the necessary instruments during the same narrow interval in which the comet passed close enough to study. Too early, and no one on Earth could have detected it. Too late, and the object would already have disappeared into the dark. That timing does not imply purpose. It reveals opportunity. The comet did not come to be discovered. Humanity happened to become capable of discovery before it arrived. Now the visitor carries most of its history away again. Its measured spectra will remain, along with the uncertainty that surrounds their interpretation. Future interstellar objects may confirm that ancient, chemically distinct planetesimals are common. They may show that 3I/Atlas was rare. Either way, this passage has established that material from another planetary system can preserve a record reaching far beyond the birth of the Sun. The real unease is therefore inseparable from wonder. A planetary system can lose an object, and the object can outlast every recognizable connection to its home. Stars move, orbits scatter. Chemical patterns remain locked in ice until another star briefly releases them. Almost everything personal to the history disappears, while a few ratios survive. At the beginning, 3I/Atlas looked frightening because it came from outside. The evidence transformed that fear. Its path was safe. Its behavior was natural. Its importance came not from what it might do to Earth, but from what had already happened before Earth existed. We watched only a small comet moving across the dark. Yet inside that moving point was a possible record of planetary construction near cosmic noon, preserved through an age longer than the entire history of the solar system. 3I/Atlas was never terrifying because it approached us. It was terrifying because of how much history had already passed before it arrived.